Hello, everyone, and thank you for joining our presentation. My name is Maja Trumic. I come from the University of Belgrade, and I'm going to present you now our work titled The Force Torque-Sensorless Joint Stiffness Estimation in Articulated Soft Robots. This work is done in collaboration with Giorgio Grioli from IIT and Centro Piaggio, Kosta Jovanovic from the University of Belgrade, and Adriano Fagiolini from the University of Palermo. Industry nowadays is dominated by rigid robots that can successfully perform pick-and-place operations. But if you look closely at this video, you would see that they do it while also exhibiting quite a jerky behavior. Therefore, we are witnessing the expansion of collaborative robots that are capable of performing dynamic contact tasks while also having a natural movement. Definitely, the main enabler for such performance is the compliance in robot joints. Here you can see robots that have a passive compliance, which is obtained by introducing flexible elements inside their joints, or we can have robots that have an active compliance, which is obtained by software solutions. Taking into account how important compliance is from the viewpoint of safe human-robot collaboration and effective dynamic task execution, in our research, we pose the question of how can we be sure that the robot has the compliance that we want it to have. And to answer that question, we start from the joint stiffness, that is the inverse value of the compliance. Joint stiffness can be understood in the following way. Let's say that we have the same robot and we change the elastic torque on its joint by the same amount. In that case, the link position will change differently depending on how much the stiffness is. So for lower stiffness, joint position will change more. Mathematically speaking, we can give here one simple example of a robot driven by the series elastic actuator. And here is the definition of its elastic potential energy, and then the elastic torque and its relation to the elastic potential energy. And from this, we can see that the stiffness is actually equal to the partial derivative of elastic torque with respect to the robot's transmission deflection. There are several pathways to find the joint stiffness value. One way is to read the datasheet from the manufacturer, or another way is to perform cumbersome offline identification of stiffness model, which includes collecting data from the encoder and force torque sensor, and then fitting the data into a stiffness model. However, if you would like to know your stiffness in real time, and if you would not like to repeat cumbersome offline procedure, then definitely you're interested in doing online joint stiffness estimation. So there are motor side solutions and link side solutions towards estimating stiffness in real time, with the difference that the motor side solution depends on precise knowledge of motor dynamic model, and it requires current sensors and encoders. On the other side, link side solutions depend on precise knowledge of robot dynamic model, and they require the usage of force torque sensors and encoders. Our solution is following the pathway of a link side approach. And to the best of our knowledge, in our paper, we propose a link-side solution that is the first link-side unifying framework for various compliant actuators. So in other words, our solution can be used for series elastic actuators, serial variable stiffness actuators, and antagonistic variable stiffness actuators. Another advantage of our solution lays in the main motivation for developing such solution. That is that we wanted to avoid mounting force torque sensors and the current sensors on a robot joint. Therefore, we developed a solution that uses only encoders mounted on link side and motor side. And to obtain a stiffness value, we follow 3 steps. So the first step is to connect the stiffness to link dynamics. That is obtained by finding the time derivative of link dynamics. Here we define a variable that is called elastic rotaton, and you can see its dependency on elastic potential energy, and then you see that it's directly connected to the stiffness value. The similar stands for all 3 actuators. Then once we have this important relation, we can estimate elastic rotaton by building upon delayed unknown input observers and by designing a known input observer that can give us that value in real time. Finally, we can estimate stiffness metrics by using a recursive least squares algorithm. And what is interesting in our solution is that recursive least squares algorithm not only gives us a numeric value of stiffness, but also it gives us an online estimation of parameters of an approximate polynomial model of stiffness that we can use even in offline regime. Let me now show you the results, starting with the simulation results and the 1 degree of freedom robot that it can be actuated with 3 different actuators. And in this third row, you can see that stiffness is well and accurately estimated in all of 3 cases. Then let me show you the experimental results that we did. First, with the 1 degree of freedom robot that is actuated by antagonistic VSA. And it's worth noting that we designed the experiment in a way that first joint position is following a sinusoidal trajectory, and then joint position is quasi-constant. And what we could observe is that in both cases, joint stiffness was successfully estimated, as you can see here. And then we repeated the experiment, but this time on a 2 degree of freedom robot driven by antagonistic VSA. And we could note that both joints had a well-estimated stiffness. So with these nice results, I would like to conclude my presentation. So thank you for your attention, and I'm looking forward to the discussion.